Welcome everyone. In this video, what we're going to look at is the other intermolecular forces. We first saw that London dispersion forces, or LDFs, are the weakest of the intermolecular forces, and they occur between nonpolar molecules. Well, now we're going to look at another one called a dipole-dipole interaction, and this one is a little bit stronger than an LDF. And this is the intermolecular force that you would see between polar molecules. You see, an LDF is when a temporary dipole interacts with a temporary dipole, which is what happens between London dispersion forces. But when you have a molecule that is a permanent dipole, and that means that it's polar, the interaction between the two is going to be a dipole-dipole interaction. And what makes a molecule polar is that one side of the molecule would be an electronegative side, which would make the molecule partially negative, as you can see here with the symbol. The other side of the molecule will be partially positive. Take a look at this example here. The blue spheres are nitrogens, and you can see that the nitrogen side of the molecule is partially negative, the other side is partially positive. Notice how the partial negative, and you can see it represented here in red, is interacting with the positive, the partially positive of the other molecule. All those red lines that you see represent dipole-dipole interactions. It's the negative end of one molecule interacting with the positive end of another. Now, these molecules are permanently dipoles. They permanently have a positive end and a negative end. They're not like the London dispersion forces where the molecules become instantaneous dipoles or temporary dipoles, and then they go back to normal and they fluctuate back and forth. These guys are always permanent dipoles. Now, look at this trend here. On the left, you have propane, which is a hydrocarbon. And notice its hydrocarbons are considered nonpolar, so the only intermolecular force that you will encounter is a London dispersion force. You'll see it's 0.1 dBs. Basically, this is nonpolar, and you'll notice it has a low boiling point compared to the other three. The second molecule, there's an oxygen there, so this little piece here is going to be partially negative compared to the exterior. So this makes the molecule polar. Notice that these molecules, all four of them, weigh about the same. They're about roughly between 41 and 46 AMUs, so they're about the same size. Notice the polarity has increased here. It's 1.3 dBs. And this molecule has two forces of attractions. It has LDFs, because all molecules have LDFs, and it also has dipole-dipole interactions. So it has both. Now, because the dipole-dipole is a stronger intermolecular force, you'll notice how the boiling point is higher. Now look at the third molecule. Also polar, but this one, you'll notice it's more polar because here, instead of the negative being in the center, notice here it's to the edge. Notice how it's much higher in polarity. You could tell by the 2.7 dBi. Now, the intermolecular forces present here are also LDFs and dipole-dipole, but because this molecule is more polar, notice how the boiling point is higher. You're seeing a trend. As the polarity increases, the strength of the dipole-dipole interaction also increases, which makes the boiling point higher. The third one, you got a nitrogen all the way to the edge here, so making this completely partially negative. This side's partially positive. Again, this molecule also exhibits LDFs and dipole-dipole, but because this molecule is the most polar with 3.9 dBs, the strength of the dipole-dipole in this molecule being higher or greater will result in a higher boiling point. So for molecules that are approximately of equal mass and size, like the ones we just saw, the more polar the molecule, the higher the boiling point will be. All right, so we have a question here. Which will have a greater effect, a dipole-dipole interaction or a London dispersion force? Well, it depends. If you're comparing molecules that are about the same size and shape, the dipole-dipole interaction will be the dominating force. I'm going to show you an example. But sometimes you'll have a molecule that's way larger, and if a molecule like a very long hydrocarbon chain, for instance, like decane or octane, even though all they have is LDFs, if the molecule is large enough, it will make that molecule more polarizable, which will cause the boiling point to be higher. Okay, so usually if they're of comparable size, a dipole-dipole will cause the boiling point to be higher because it'll be the dominating force. But if a molecule is very large, the LDFs will probably take over as the dominating factor, and that will determine physical properties such as boiling and melting point. In this example, we have two molecules of comparable size. You can see the molar masses are basically the same. However, ethane on the bottom is a hydrocarbon, so the only thing here is LDFs. But when you look at formaldehyde, you got a partially negative here and a partially positive. You got a dipole here. So this not only has LDFs, this also has a dipole-dipole. So this one possesses two types of intermolecular forces. Now, again, if you are comparing two molecules of about the same size, the dipole-dipole force is a much stronger intermolecular force. So notice how the boiling point is way higher as well as the melting point compared to ethane, which is only determined by LDFs. So the dipole-dipole interaction will result in a higher boiling point as well as a higher melting point. Now, there's something strange that we're going to talk about, okay? There's a special type of dipole-dipole known as a hydrogen bond. And you'll notice here the question asks, what does this graph show us? And you're going to see we're comparing elements from several groups, from group 4A, 5A, 6A, and 7A. And you're going to notice that group 4A, which is represented on the bottom in orange, is the only one following the expected trend. Notice, and I'm going to show you a close-up, that as the molar mass increases, notice how the boiling point also increases. So if you look here, the group 4A elements on the bottom in orange, this is the normal trend. You got, if you're looking in the periodic table, you're looking down the group. So you're comparing carbon with silicon, with germanium, with tin. And notice that the molecular weights are increasing, and so is the boiling point. But then when you look at the group 5, 6, and 7 elements, the first element of that group, which belongs to period 2, that would be nitrogen here, that would be fluorine here, and oxygen here. Notice that they are anomalies. They are not following the trend. You see, nitrogen should probably be somewhere down here, and it should go like this, okay? Oxygen, the same thing. It should probably be somewhere down here, and fluorine should be somewhere as well down here. They should all be lower, and it should be gradually going up. Yet, with oxygen, fluorine, and nitrogen, notice how the boiling points are unusually high. Okay, you can see them right here. And then the rest of the group follows the same trend. So let me pick the halogens here for a moment. So you got HF, okay, then after HF, you got, chlorine would be underneath. That would be, the halogens are the ones in green. So then you got here, this would be the chlorine, then bromine's over here, and then you got iodine over here, and the molar mass is increasing. You would think the boiling point goes like this, yet this one has the highest, higher than these three. So there's an explanation, okay, why these three don't follow the pattern. The explanation is something called hydrogen bonding. It's a special type of dipole-dipole interaction, and it's experienced when a hydrogen is directly connected to a highly electronegative element, but it's only nitrogen, oxygen, and fluorine. Notice in the pictures that the hydrogen represented in red is directly connected to either an O, an F, or an N. The hydrogen being the positive here, and these being more electronegative. There's an interaction between an H and an O, F, or an N. So here you got H interacting with O. Here you got an H interacting with an F, H interacting with an N, and there's a couple more examples on the bottom. These interactions are known as hydrogen bonds. They're represented by dotted lines. That's why I drew them. And you'll notice the hydrogen atom has to be directly attached to a highly electronegative atom, which would be H, F, and N. And that interaction will occur with a nearby small electronegative atom, such as O, F, and N, attracting to an H. In other words, a hydrogen bond is when an H interacts with either an O, an F, or an N. So you have two waters here interacting. Waters interact through hydrogen bonding. You'll notice here hydrogen interacting with fluorine. Okay, hydrogen interacting with nitrogen. Here you got, doesn't have to be the same two molecules. It could be a water with an ammonia, but you could still have a hydrogen bond here. Notice the H is connected to O and it's interacting with an electronegative element. And here you have it drawn the opposite way. Okay, now the thing about a hydrogen bond is it's a lot stronger than a regular dipole-dipole. Okay, so you'll notice again, here I'm showing you how highly electronegative the nitrogen, oxygen, and fluorine are. This will be the negative side over here. And the hydrogen side obviously will be the positive. And we're going to represent that with a dotted line. And what you're going to notice is that they are unusually very strong intermolecular attractive forces. They're much stronger than dipole-dipole. They're much stronger than dispersion. And because it's a much stronger intermolecular force, it's really like a glorified dipole-dipole, a way stronger dipole-dipole. They will have higher boiling points and higher melting points than similar things that cannot hydrogen bond. Now, keep in mind a hydrogen bond is still an intermolecular force, so it's not as strong as a regular chemical bond, such as a covalent bond or an ionic bond. Those are intramolecular forces. In fact, although hydrogen bonds are pretty good intermolecular forces, they are only 2 to 5% of the strength of a covalent bond, which kind of puts in perspective how weak intermolecular forces are compared to intramolecular forces. Okay? So here we got two examples. Again, you'll notice that they are of comparable size. They have about the same molar mass. But ethane on the bottom is completely nonpolar. The only thing it does is LDFs. Now, methanol also does LDFs because they all do. You can even put it does dipole-dipole, okay, because it is polar. But there's something special. Let me fix that. There's something special here. Okay, let me fix this. Okay, so what's special is because this H is directly bonded to an O, this H can participate in hydrogen bonding. So this one has all three types of intermolecular forces. Now, the most dominant one is the hydrogen bond, and that's going to explain why the boiling and the melting point are significantly higher than ethane, even though they have about the same mass. Okay? That high boiling and melting point is due to hydrogen bonding. Here's another example. If you look at ethanol at the top and dimethyl ether, notice they are isomers of each other. They have the exact same molecular formula. But when you analyze the structural formula, you're going to see that ether over here, or dimethyl ether, has LDFs. But it only does dipole-dipole. And if you're wondering, well, there's hydrogens there, there's an oxygen. In order to do a hydrogen bond, there has to be an H directly connected to the O in the middle. There isn't. That's why this cannot do hydrogen bonding. Now, when you look at ethanol, and we go ahead and draw the structural formula, okay, you're going to see that the H is connected directly to an O. So, yes, this does LDFs. We can also say it does dipole-dipole, which it does. But it is important that you mention that this one also participates in hydrogen bonding. And because it participates in hydrogen bonding, even though they have the exact same molar mass, look how much higher the boiling point is, and look how much higher the melting point is as well. So hydrogen bonding does affect the boiling and melting points, making them much higher. Now, the last type of intermolecular force, which is actually stronger than a hydrogen bond, is called an ion-dipole interaction. And these are found in solutions of ions, especially what we call aqueous solutions. Aqueous solution simply means an ionic compound dissolved in water. So what you're looking at here is NaCl, which is an ionic compound. When placed in water, water's going to split this. And what's going to happen is, and you're looking, this is a water molecule. You're going to notice, and I'm going to show you a better picture here. Notice how the chloride ion, which is negative, is surrounded by the positive side of the water, which is the hydrogen side. Notice that that dotted line represents an ion dipole. You see, the chloride is a complete ion, and water is the dipole. Dipole is just another word for polar, because water is a polar molecule. Notice on the other side, you got the cation, which is sodium, being positive. Notice how it's surrounded by the waters. Notice they're oriented in the opposite way. The oxygen side of the water, which is negative, is interacting with the cation. And again, this is an ion dipole. Now, when you have water by itself, the boiling point of water is 100 degrees Celsius. And that's because the only intermolecular force you're breaking are hydrogen bonds. Well, you got LDFs and dipole-dipole, but the main force that causes the water's boiling point to be 100 degrees Celsius is due to hydrogen bonding. You got to break all those hydrogen bonds so that the water can escape as a gas. But if I add salt to water, I now introduce ion-dipole interactions. So I don't know if you know this, but when you add salt, let's say, to water, the boiling point no longer is 100 degrees. It's actually higher. Maybe it's 100, let me fix this. Maybe it's 102 degrees or 103 degrees. You know, it depends how much salt you add, but the boiling point will be higher. And the reason is because now you're not only breaking hydrogen bonds, you are also breaking ion dipoles between the salt that you added and the water. So in addition to breaking hydrogen bonds, there's an extra intermolecular force that you're breaking, which happens to be the strongest of the four, called ion dipole interactions, and that raises the boiling point even further. So let's summarize how we determine intermolecular forces. All right, so we're going to start with this question at the top. Are any ions present? If you answer yes, and we're going to focus on the right side of this chart, then you're going to ask a second question. If there's ions present, then you ask, are there polar molecules present? If it's just ions, no polar molecules, then it's an ionic bond, just like NaCl. Okay, the Na is positive, the Cl is negative, and this is actually an intramolecular force. This is not even an intermolecular force. It's basically ionic bonding. And notice how the energy is extremely high because it's an intramolecular force. The strength is greater than 150 kilojoules per mole. Now, if there's a polar molecule present and ions as well, so you got the two now. In the first case, it was just ions present, but now you got an ion, okay, with a polar molecule like the example we saw here. Okay, that would be this case. So if you answer yes to that, then you got an ion dipole force, not as strong as an ionic bond. It's an intermolecular force, but it is the strongest of the 4 intermolecular forces. Notice the energy is not as great as 150, but the energy is greater than 50 kilojoules per mole. Now, let's say there are no ions. So if you answer no, then you ask yourself, are polar molecules present? So if there's no ions and there's nothing is polar, you're looking at a plain old LDF, London dispersion forces. These are the forces of attraction between nonpolar molecules such as hydrocarbons, all diatomics. They're all nonpolar. Notice they are very weak at 0.1 to 30 kilojoules per mole of energy. Okay, this is the strength. Now, if there's polar molecules, then you gotta distinguish. So you answer yes, there are polar molecules. Now, if the polar molecules do not have hydrogens attached to an N, an O, or an F, if you don't see that, a hydrogen directly attached to an N, O, or an F, it's a simple dipole-dipole, like HBr they show you there, okay, an HBr with another HBr. There's an interaction here because this side is more negative, this side is more positive. That's a regular dipole-dipole. However, if a hydrogen is attached directly to an N, O, or an F, in other words, if you answer yes to this question, such as this one here, then this dipole-dipole interaction is much stronger, and we call that one a hydrogen bond. Notice the energy, the strength for dipole-dipole compared to a hydrogen bond is way stronger. Okay, so these first 4 here are intermolecular forces. This is an intramolecular force. And don't forget that the first 2, dispersion forces and dipole-dipole, are collectively known as van der Waals forces. Now let's do a quick summary. Dispersion forces are the weakest of all the intermolecular forces. They're known as LDFs. Okay, and they're present in all molecules and atoms. Every single atom, every single molecule will have a dispersion force. They are predominantly only found between nonpolar molecules, but all molecules possess this. Now, the magnitude of dispersion forces will increase with molar mass. If you recall, as the molar mass increases, the molecules have more electrons, or the atoms have more electrons. The more electrons, the more polarizable the electron cloud can get. Polarizability is distortion of the electron cloud. So the more polarizability, the stronger the LDF, which will result in a higher boiling point. Okay? Now, polar molecules, in addition to LDFs, they also possess another force called the dipole-dipole attractive force. And a dipole-dipole is much stronger than an LDF. But then you have a special dipole-dipole called a hydrogen bond. It's the strongest of the 3 intermolecular attractive forces when you're looking at a pure substance. Okay, like a water with a water, or an HF with an HF. Okay, and a hydrogen bond only is present when a molecule has an H directly connected to an oxygen, nitrogen, or a fluorine atom. Now, the only example of fluorine that hydrogen bonds is an HF with another HF. Okay, so keep that in mind. That would be the only way that HF can hydrogen bond. And then we got an ion dipole attraction, which is a 4th intermolecular force. This one's present when you have a mixture of an ionic compound with polar molecules. The best example is an aqueous solution. An aqueous solution is basically an ionic compound. You're dissolving it in water. Water's your polar molecule or your dipole, and then the ionic compound is the source of the ion. Ion dipole attraction would be the strongest of the 4 intermolecular interactions, and they are very important in aqueous solutions of ionic compounds. This is what allows ions to dissolve in water. Now, here is a table illustrating the 4 intermolecular forces. You'll notice that the first one you got two diatomics. You got hydrogen and hydrogen. They're both nonpolar. So the only intermolecular force between hydrogens will be an LDF, a London dispersion force, and that's the weakest of the four. These are going to have low boiling points, low melting points. In fact, hydrogen is a gas at room temperature. Now, as we go down, you'll notice the next one, you're looking at two polar molecules. HCl is polar because chlorine is more electronegative. Notice how the chlorine side is more negative than the hydrogen side. And you'll notice that the partial negative and the partial positive, there's an attraction there. That attraction is called the dipole-dipole force. It's stronger than an LDF, and it's what occurs between polar molecules. Then you have a special dipole-dipole, and this one fits the criteria. Notice how the H is directly connected to either an F, an O, or an N. Here it's connected to an F. So notice how the fluorine side is the negative side, the hydrogen side is the positive side. And although it looks just like a dipole-dipole, because it really is, this one's unusually stronger, and we're going to call this interaction a hydrogen bond, and it's much stronger than dipole-dipole or dispersion forces. And then finally, when you have an ion dissolved in, let's say, water, and you form an aqueous solution, you're going to form an ion dipole. The ion, the example I used was NaCl. You'll notice that the cation, which is positive, will interact with the negative side of the dipole. In water's case, it's interacting with the oxygen side of the water, which is partially negative. When you have an anion, remember that that one is going to interact with the hydrogen side of the water, which would be the positive side. And the ion dipole interaction is the strongest of the four. Okay? So all of these are your intermolecular forces. They do determine many physical properties. We took a note how it affects boiling points. Later we introduced melting points, but it does affect other physical properties as well that we will take a look at in the next video.